All right, appreciate it. I don't know what that green line is.
What green line?
Well, on my screen here, there's a kind of a green square keeps showing up.
Showing the portion that share.
Are you seeing it?
Not for me. I mean, like you are viewing Robert Luke's screen. Is that the green line you're talking about? Because that's the only one I see. Just means it's sharing a screen.
Huh.
Yeah. And it goes away.
Well, I must have done something wrong. I'm not sure why it's there, but hopefully it's kind of covering up some letters.
Yeah, I see that on the far left there.
I think it's related to the sharing, so like the new share.
Well, I stopped unless I've got another share still going. Let's see.
We go into the one. You got your green line back.
No. Maybe that was it. I didn't have it. No, no. Hate computers. See if we can start from.
Got it.
All right, it looks better. Okay, so we're going to talk about semiconductors and talk about diodes and transistors. Most semiconductors are primarily made from either silicon or germanium. You don't see many germanium, some small signal diodes, they still make out of germanium. Majority of semiconductors, except for very special purpose, are made from silicon. There's three types of silicon that are used. One we call intrinsic, which is basically pure silicon. And it's actually an insulator. We have P-type and N-type silicon, where we add impurities to the crystal. Silicon is a crystalline structure, and you actually can grow them. And by putting certain impurities in, we can give it a positive or a negative charge, which we'll show in a little bit. And because it's a semiconductor and you have those charges, if you remember, we talked about the band gap for semiconductors where there's separation. It takes a certain amount of energy or voltage to have charge cross that gap. In the case of silicon, it's approximately 0.7 of a volt or 0.7 volts. And in the case of germanium, it's 0.3 volts. those are important numbers because they're on the test. Or maybe. When we talked about pure silicon, okay, it has 4 valence electrons, so it's in that semiconductor range. And if you had chemistry and you learned about covalent bonds, when it forms a crystal, those 4 electrons in the outer shell can kind of be half and half, halfway in one atom and half in the other, and vice versa for the atom in that one. So they call that a covalent bond, because you have an atom or an electron in each atom sharing the same valence shell between the two. And that's how the crystals physically bond together. When we take an added impurity, okay, one of the typical ones is add boron. It only has 3 valence electrons. So you can see when we slip those in there with the silicon atoms that have 4, we got a hole. It makes it positively charged because it's missing basically an electron to fill the shell. If we add something like phosphorus, or I think antimony or an arsenic or other similar ones, they have more electrons in the valence shell. So we wind up with a negative charge. You can see over here the little red guys, and you got one, it's kind of like the thing where they plays music and you run around the chairs and sit down and they keep taking chairs away. Well,
Musical chairs.
yeah, didn't have a chair to sit in. So that's how we get the 2 types, the P type and the N type. And that's what we make semiconductors out of. Actually all 3, because we tend to use the intrinsic silicon as the base, since it acts as an insulator. So the very first semiconductor that was developed is a diode, which consists of some material that's P doped and some that's N doped that are joined together. There's a junction. And we apply electrodes, and we call those the anode and the cathode. On the physical package, we'll mark the cathode with a stripe. And I think I have a chart showing a picture of what some of them looks like. When we forward bias the diode, which means we apply a positive voltage on the anode, which is connected to the P-type material, and the negative conductor connected to the cathode, that will cause a current to flow from the anode to the cathode through that diode, assuming that the voltage is greater than 0.7 volts if it was silicon, or 0.3 volts if it was germanium, because it takes that amount of potential for it to cross that barrier. And we call that forward voltage drop. If we reverse it and we put negative on the anode and positive voltage on the cathode, it will not conduct. I won't go into this a lot, but basically what happens is when you put these 2 regions together at that junction, you'll have some migration where the positive and negative will combine, and we call that a depletion layer, because there's no, or there's a, shouldn't say no, but there's very few positive or negative charges. They're on either side of it. When we apply that voltage in the positive direction, from the P being positive and N being negative, that depletion layer actually shrinks a little bit. And it allows, once you have enough energy to cross over that depletion region or that gap, it allows current to flow. When you reverse the polarity, it causes the depletion region to grow. So it makes it much, much harder to conduct current. Now, at some point, with high enough voltage, it will. And that's called the Zener effect. And this is just kind of showing the same migration. This is this typical symbol that you see for a diode, with this triangle pointing to a little bar, which is the cathode. The triangle is the anode. Again, showing the same thing, and what the two junctions sort of look like, where you've got electrodes attached to the P region and the N region. And if we plot the current versus voltage on the diode, if you see, we have a forward voltage, we have just a small leakage current until we get up to what we call the knee, which for silicon is around 0.7 volts. And then it will start to conduct. And the slope of this line is going to be a function of the series resistance. When we go in the opposite direction, you're still going to have some leakage current in the opposite direction. And these are very small and microamps. Until it gets up to the Zener or breakdown voltage. And then it will conduct at even less resistance than it does in the forward direction. And we use that effect to create what we call Zener diodes, where we actually use those in reverse direction. And they can be manufactured so that that Zener effect is at specific voltages. So you can use it as a voltage reference. You can have it for 10 volts or 5 volts or whatever. And it makes a very good, stable voltage reference. This is a typical, in this case, this is a little small signal diode. It's in a glass package. You can actually see the little junction in the middle there. And the black mark or stripe indicates that's the cathode end of it. So what electric component allows current to flow in only one direction?
Charlie.
What are the names for the electrodes in a diode?
C.
Charlie.
What are the names for? What?
C. Electrodes in the diode.
Charlie.
Oh, okay.
Oh.
I backed up on that previous one. How is the cathode lead of a semiconductor diode often marked on the package?
B.
Bravo.
Bravo. That's not always true, but most of the time on small ones it is. What is true about forward voltage drop in a diode? The tricky one.
Which is
No.
Hmm?
No.
Bravo.
You think it's Bravo? Says peak,
Partial peak
peak inverse voltage would be reverse voltage, right? So that wouldn't give you a forward voltage drop.
and peaked on the voltage. Diver.
How about alpha?
Sometimes.
And it's,
Can you explain that one to us then?
well, germanium diodes have a 0.3 volt forward voltage drop. Silicon has 0.7. That's why the question was, what is true about forward voltage drop in a diode? Some have lower than others.
So that's the amount.
Oh, okay.
To
Germanium.
over-
How much voltage it takes for it to start to conduct.
Yeah, for it to start. Yeah.
Do they make variable diodes? Like variable capacitors, variable potentiometers, and like do they have like a variable diode that you can I don't know. Is there such a thing?
Well, actually, we'll talk about that next. It's called a transistor.
Oh, okay. Yeah. Okay.
So, but first we're going to talk about light emitting diodes, which is a special type of diode that they take advantage. I think I mentioned before that when free electrons recombine with an atom, they have to release that excess energy, and it's in the form of phonons, which have a frequency proportional to the amount of energy. And it turns out that a regular diode, like we talked about, when it's conducting current, that recombination is going on and they're actually producing light. So if you had put that regular diode in a clear package, like we do with an LED, you would see a little bit of light emitted. So when they discovered that, they also discovered that they could use different materials other than silicon or germanium. And they use things like gallium arsenide phosphide and gallium phosphide and some other things on top of that to enhance it. And create different colors. So that's how you get all these different colored LEDs. Because as they conduct current, they produce light at different wavelengths depending on the type of material. And the thickness of the layer also determines the frequency or the amount of energy. So they can generate anything from infrared all the way up to beyond ultraviolet nowadays with these light emitting diodes. And when it's like a regular diode, when it's forward biased, which means positive on the anode, it will conduct and emit visible light. Now, because it's not silicon or germanium, they have different forward voltage drops. And in some cases, they may be up 2 or 3 volts. Depends on the material. In fact, like every color LED is going to have a different forward voltage drop, which is just something you have to take into account when you're doing a circuit with them. Essentially, they're used as some sort of indicator. If you put a bunch of them together to make some kind of digital readout, or individual indicators like power's on or some kind of fault or whatever, but essentially they're used as indicators. This is just showing how they generate some of the different colors, and you can see I get that out of the way. The different forward voltage drops for different where they start to knee, although it's not very sharp. So what causes a light emitting diode to emit light?
Oh,
Which of the following is commonly used as a visual indicator?
Alpha.
Alpha. All right. Transistors are your variable diode.
Oh, okay.
We can use a transistor to control current flow, where we had no control on the diode. It either conducted or it didn't. With a transistor, we can vary the amount of current flow through the device. And again, we make it from doped semiconductor material, P-type and N-type. We basically have two types of transistors. There's a bipolar junction transistor, which is a current-driven device. And there's a field effect transistor, which is a voltage-controlled device. In both types, we have like positive and negative, NPN and PNP, which represents, since it's actually three pieces of material. For a bipolar junction NPN transistor, there's a piece of N material separated by a piece of P material from another N. If it's a PNP, it's the opposite. It has P material on each side and N material in the middle. So there's two junctions. The field effect is slightly different, and it creates a channel through one of the semiconductors, and the voltage on the control element, which is called the gate in this case, can vary the amount of current through that channel. So it can either allow maximum amount or pinch it off to zero. In the first type, the bipolar junction, it's made up of these three types of material. It has electrodes called emitter, base, and collector. The collector is the normal positive connection. The emitter is normally your negative connection, and the base is the control element. So you apply a voltage between the base and the emitter. If that, that part works like a diode. You can see there it's a PN junction between the base and the emitter. So as you apply a voltage to the base, when you get over the forward voltage drop, because it's the same kind of silicon junction, so at 0.7 volts, it will start to conduct through this PN junction like a diode. If there's a voltage also on the anode, that can cause an avalanche effect and cause current to also flow from the collector to the emitter. And how much current flows is proportional to the current flowing from the base to the emitter. And there's a kind of a gain factor, and it's actually dependent on how thick this P layer is. The thinner it is, the higher the what they call the transconductance. So the more current from collector to emitter per unit of current from base to emitter. And a lot of times we refer to that transconductance as the beta, or the gain of the transistor. So if it had a gain of, say, 100, that means if I had 1 milliamp coming through base to emitter, I would have 100 milliamps from anode to, or from collector to emitter. If I make it out of the opposite layers, a PNP, it works in a similar fashion, except we just reverse the voltages. So you need to remember it's has an emitter, a base, and a collector. The symbols look like the circle. The horizontal bar there is basically the substrate, which would be intrinsic silicon. You have the base connected to the center piece of material, and then your collector and emitter. In the case of an NPN, you see the little arrow showing current coming out of the emitter. In the case of PNP, you're going to see current coming into the emitter because it's reverse polarity device. If you look at a cross section of how one of these is actually made, they don't physically glue these things together. They actually grow them this way. I don't understand the whole process of how they manage to do it, but they can take the silicon crystals and dope them with impurities in specific areas like this and create this kind of a cross section and then make physical contacts to those areas. This is showing the three areas, and I mentioned the depletion zone. They also have a depletion zone. It works just like it does on the diode. And as you put a positive voltage between the base and emitter, it decreases that depletion zone. If you would reverse it, it would widen it, and it would reduce the amount or cut off the current flow from the collector to emitter. I mentioned transconductance, and that's where you get the gain in the transistor. For a small amount of change on the input, you see this much larger change on the output. So the slope of this line is the gain or the transconductance. So which of the following components can consist of three regions of semiconductor material? What are the names of the electrodes of a bipolar junction transistor? Bravo.
Right.
Field effect. Now, the bipolar was a current device, so we applied current from the base to the emitter. In the case of the field effect, it has three terminals called gate, drain, and source. The gate is the control element like the base is on the bipolar, but we apply a voltage to the gate because we're going to create an electric field that will control the current flow between the drain and the source. We also have two types that can have a P channel or an N channel. And the voltage, the polarities change just like they do on a field effect. The basic difference is instead of using base to emitter current to control it, we use an electric field. So there's very, very little current involved. It's essentially a voltage device like a vacuum tube. That's the way they work. The diagrams that you'll see for field effect transistors, and there's some variations of these, but this is the basic one for like a junction field effect. And you see you've got a drain, a source, and the gate. In the case of the N channel, okay, we're showing, in this case, electrons coming in. Show it in the opposite direction for the P channel. When we look at kind of a cross section, you can see that this N channel device with the P on each side that the gate is collected to or connected to, is creating an electric field between these two. And that kind of purple area is showing how it can sort of pinch off that region. And that's how it controls it, by controlling how many electrons or charges can flow from one end to the other. So as that restricts it, okay, it reduces the amount of current. And as it opens up, typically if there's no voltage there, you're going to get maximum current flow. If you have in this one a high negative, it will shut it off. This is showing how the current flow varies for different values of gate to source. So you see at 0 volts on the gate, we have saturation current, the maximum amount of current that it'll conduct. As you go more and more negative on the gate to source, you have less and less current flow. So that's how you, by applying a varying voltage between 0 and, in this case, like -5, you could actually use it as a switch to turn it on or off, or vary it somewhere in the middle as an amplifier. Another variation of the field effect is the metallic oxide semiconductor, where the gate is separated by an oxide layer. You still have a field. It works the same way, and you wind up with this channel. And that electric field will control the width of that channel. And I'd say most of the field effect transistors in use today are the MOSFET type. What does the abbreviation FET stand for?
Delta?
Go along with that, Rick?
See?
You want to make sure you're awake.
Oh, I'm awake.
What type of transistor has a gate, drain, and source?
That'd be D2, bipolar junction.
Gate, drain, and source.
Field.
Gate drain and source.
Not base emitter collector.
Well, this would be B. Field effect.
There you go.
B.
Okay, so how do we use transistors? Well, we can use them as switches, which is what you do in digital logic, basically, where you either have them totally on or totally off, operating in what we call saturation or cutoff mode. If you want to use it as an amplifier, you bias it up somewhere in between those two values, and depending on the slope of that line that we saw earlier determines how much gain and how much the output current changes, or the current through it, proportional to the control voltage or current, depending on whether it's a bipolar or a field effect transistor. And we define gain as the ability to amplify the input signal. So if I have 1 volt in, 10 volt out, I had a gain of 10. This is showing a similar chart to the field effect for a bipolar. And each of these horizontal lines is a different amount of base current. So in this case, as we increase, if we have no base current, we're going to have no current flow. As we increase the base current, the current from collector to emitter increases. They're kind of the opposite of the field effect. Which of these components can be used as an electronic switch?
B,
Charlie,
Charlie.
B.
What's the term that describes a device's ability to amplify a signal?
A,
Jumped on that one.
hey, good, good.
Which of the following can provide power gain?
transform.
I would say alpha.
Have we talked about transformers?
No,
Well, then how do you know about a transformer? You're guessing.
Voltage
bravo. Bravo.
gain, reactance.
And we know resistors don't have gain, right?
So it
Yes.
can't be a transistor.
A resistor would have power loss.
There's no transistor.
So it'd be a transistor. Transformers
Power.
can have voltage gain or current gain, but they can't have power gain. Power ins, power out.
Transformers are usually either to go from a high voltage to a low voltage.
Right, they can transform a voltage, transform.
Right.
But if I increase the voltage, I decrease the current, so the power, which is the product of the two, is the same. Except there's some loss, so I actually get slightly less out than I put in. So we learned that diodes can conduct in one direction, except for the Zener effect. That the forward bias for germanium is 0.3 volts approximately and 0.7 volts for silicon. If you notice on that graph, it actually varies depending on the device. And in some cases, it might be 0.6 or it might be a little more than 0.7. A lot of variables, but approximately 0.7. And that's what they use on the exam. Diodes have an anode and a cathode, and the cathode end has normally a stripe on it to indicate that it's the cathode. Light emitting diodes are special diodes that they're made to emit light of different colors when they're forward biased. Transistors can give you power gain, or they can be used as switches. Bipolar junction transistors have a base collector and emitter. And field effect have a gain, drain, and source electrodes. Oh. Oh.